vector that is a local variable inside the function. It's completely separate from what was in the main program. It's just that it has the identical content to what is in your main program. Okay, some code that illustrates this. I make a vector v, I set v0 to 3.5, and then I call a function set0 where I give my function. Set0 is defined as take a vector and a value and set that value in location 0. Okay, but because this is passed by value, it creates a copy of the vector. And so you pass v, you pretend to set element 0, but if you print it out, you don't actually get 4.6, you get 3.5. Because passed by value passes a copy. If you would have passed your vector by reference, then, not sure where that output went to. It should have said 4.6. Right, so pass by value, pass by reference. And if you want to pass by reference because you want to save on copying, but you want to prevent yourself from accidentally changing it, then do a const reference. Okay, no need for pointers here. References are much better. Michael, if we use a ref to vector, then we are passing in and out of the function, address or copies. It just uses addresses. Nah, probably, but a reference, yeah, it deep down it uses addresses, but a reference is not an address. A reference is an alias. So it's a second name that acts like it is the exclusive owner of something in memory. But yes, if you declare vector float v, then it's passed by value, so the whole object gets copied into the subroutine. If you use a reference, then the v in the subroutine becomes a reference to the v in the main program, meaning it's two names, both v, but pointing to the same object. But v is not really an address in the technical sense, because v dot means that v is an object of which you do the add method. I'm trying to see where it copies the whole object and where it just manipulates. Yes. So use references so that the parameter of the function becomes an alias of the actual argument. So use the ampersand if you actually want to alter the array, or if you want to prevent copying. And if arrays are short, I wouldn't worry about it, but for big arrays, yes, do worry about it. So you use an ampersand, and since you seem to be concerned about performance, I'm sure you'll be using ampersand left and right, but then really I would stress that you use const as much as possible to indicate that yes, I'm passing by reference, but no, I am not going to alter the array. This prevents a this prevents a world of trouble. Okay, vectors in classes. Can you make a class around a vector? Yeah. Okay, so you're doing your physics, and you have a vector field which contains a vector of values, but it also has a name. So for purposes of output or so, you want all your vectors to have a name, and so you make a class thingamy that has the actual values, but it also has a name. Okay, and you can imagine that this is useful. Now the problem is, so when you create a named field object, who is going to create this vector, and when is it going to be created? So there are two different ways of doing it. The less desirable way is to use the constructor. So so the class named field, and you have a constructor where you tell it, okay, what is the size of my vector going to be, and then you do values is a vector of int. Okay, what happens here? As soon as you call the constructor, it will create an empty vector, and then you create a new vector which you copy over the empty vector, and so the empty vector is sort of wasted. It was created for no reason. So that's a little inefficiency in your program. The preferred way of doing it is like this. So your constructor takes an int, and then it uses an initializer list where it creates the vector of the right size and immediately puts that in the data member. So there is never an empty vector that is being created. Okay, so this is an idiom that you sort of need to internalize. Initializer lists are a great idea, and in fact they are more efficient. In the previous examples, there was no real difference between copying it and using initializer lists, but here using the initializer list puts this vector straight into this object as it's being created. So there is never an extra vector created and then immediately thrown away. Okay, so this is how you make a class that contains a vector. Multi-dimensional vectors, yeah, those are tricky. You could do the following. You could create one vector which you call row, and then you make a vector of vectors, rows, which has 10 times. And what was this? What was this syntax again? What is this row doing here?
Is it the type?
Nope. No. Okay, so you have a vector of angle brackets. So the type is here. Ju1 had the right answer. It's the initial value. So this notation, so ignore everything to the left of my highlight. So this means rows is a vector of length 10, and each element gets initialized to row, where row is itself a vector. And so now you have a vector of vectors, and each of these is initialized to that row thingamy. You can also do the following. You declare a vector of vectors of a certain size, and then you set them in a for loop. That is more flexible if you have, if not all the rows have the same length. But both of these are, yeah, Can anyone think why this may not be a good approach? What is the problem with having a vector of vectors like this? In C, if you make a two-dimensional matrix, where is that thing in memory? How is that allocated? Is that here a row, there a row, there a row, there a row? By row? Yeah, that is part of the answer. So, so some C programmers are under the misapprehension that this is the same as what is the syntax? I'm taking some shortcuts. Some C programmers think that a multi-dimensional array is created like this. It's an array of pointers, and then each pointer is set to a consecutive. I hope no one thinks that this is the case. This is really int star x is malloc 5 times 6 times size of int. Yeah, so in C, a multidimensional array is really a single star pointing to a contiguous array. Yeah, a contiguous row. Yeah. So, question: why is x sub 1 of type int star? See, x is of type int star. So x1, why is that of type int star? Yeah, that's tricky stuff in the standard. Michael, alloc first level column pointer and then allocate. Yeah, okay, I forgot this one, right? But the int 5.6 is equivalent to a star and not to a star star. Why am I mentioning this? Okay, so I'm mentioning this because doing a vector of floats is really the same as having an array of pointers. Now, why? In both cases, I can now write x sub I sub j. That works in both cases. So why don't I like the double star? Why don't I like the vector of vectors? Well, doing these separate mallocs puts the rows of the array in different places in memory, not necessarily adjacent. So even though to the programmer both of them look like this, from a point of efficiency, and now we're getting into the level into cache and locality and cache lines and basically everything related to performance. For performance reasons, the double star is a really bad idea. And so the same holds here. Your rows are not consecutive in memory, which is not good for performance. And so what you actually want to do, by the way, I don't know how many people here align the beginning of each row. Yeah. You're right, Michael, but that's not the main point. I could have here instead of malloc, I could have done POSIX mem align, forget the syntax, 16 or something, and it would have been just as bad. You're right about alignment, but that doesn't take away the fact that it's randomly in memory. Okay, so how do you do multidimensional vectors? C++ is just not a scientific programming language. Ooh, did I just say that? Well, I mean, it's not Fortran, which was designed from the beginning to do Cartesian thingamies like scientists like to do. So, okay, so if I want to write a matrix class, I can say, okay, I store my elements in a vector of doubles, and I create that stuff, and I write a set routine with ij and a value. I write a get routine that gives me the elements, and I get fairly elegant code. But really what you want to do is, instead of having a vector of vectors, do a single vector. And then inside your get routine, instead of getting elements at, why is this not selecting? Instead of getting a two-step at, you do a single at where you have a indexing expression. Okay? So yeah, C++ has no support for multidimensional arrays, not any more than old style C stuff. And so, but with object-oriented programming, you can actually make it pretty cool looking. You can even improve on this a little more, but let's keep it like this for now. Yeah. Huh. Okay. When I teach this as a semester course, there is now an exercise, do Pascal's triangle. So instead of allocating a matrix, you need to allocate a triangle. So you need to think about how to do that. Feel free to do it at home. Send me your solution over email. I want to go on to the next couple of topics. Okay, so vectors. As long as you don't do anything dynamic, they are as efficient as C arrays, and they are much more consistent and easier to program and all that. So no more C arrays. Definitely no C character buffers. Half of all security bugs, or at least half of all security bugs, come out of string mismanagement. C++ strings and then certain improvements in C++20 are a big improvement on this. Okay, include the string header using standard string. And now you have the keyword string. So you can say string, this is text. There is a copy operator which really makes a duplicate. It's not copy the pointer, it's copy the contents. Strings. So string, my string, space, my string is foo. My string plus n is space, plus n is bar. Oh, isn't this wonderful? Now you can actually do string concatenation without having to code it out yourself and without having to worry about the null delimiter and all that sort of 1970s archaism. Okay, strings, really nice. Strings are again a class, and they act very much like the vector class. So they have a size method, and you can index in it with square brackets and with the add method. So strings are almost a derived class from vectors. Not quite, but they have the same method: insert, erase, push back, and then there are a couple of methods that only exist in the string class, like find. So that's finding a substring. You can imagine that finding a substring in an integer array means nothing. Well, I guess it means something, but it's not useful. Anyway, so strings are a derived class from vectors. And so in addition to all the base methods, they have a couple of methods like find. Okay, so don't use C-style arrays, use vector or maybe array. And don't use C character buffers, use strings. I/O, nah, I don't want to go into this. So this cout stuff is kind of simple because it uses default formatting, and it's kind of cumbersome with all the little then signs. I'll just mention a couple things that you can do with it. So if you print numbers and they go up by a factor of 10, you get the default format. If you use the IO manipulation header and you include the set width function, then you can, yeah, this is not terribly nicely formatted. Now you have the same loop and you print the numbers, but you set the width to 6 characters, and then you see that the output becomes 6 characters wide and right aligned until it overflows. What happens in Fortran when it overflows a format specifier? Anyway, so if you want to print numbers nicely as a table, use the set width and you'll be happy. No Fortran programmers here? Let's see. So in this right alignment case, it used spaces to fill it in. You can also set fill and fill it with arbitrary other characters. Yeah, what am I doing here? Instead of right aligning, which is a default, I'm using left aligning, and you get this. You can set the number base, and so this is a table of the first 256 numbers, and you see that when you go over 90, you get A0, etc. Exercise if you want to do it at home. There's fixed point. There's scientific notation. So there's a bunch of things you can do, but all of this is going to be improved when the C++ Standy 20 standard has been implemented. It was ratified somewhere mid last year, but of course that doesn't mean that immediately all the available compilers support it. Okay, so all this stuff was about screen output. If you want to output ASCII to a file, then instead of IOStream, you do FStream. And now you make a file stream and you open it to a file. But, and this is really nice, now all this less syntax that you learned for cout works the same way. Cout is a stream that goes to your, C stands for console. So cout is a stream that goes to your screen. And if you use a output file stream, then you use the same syntax, but now it goes to your file. And it's pretty elegant. Well, it's the same with printf and fprintf, right? I'll leave this, and all this I/O stuff is going to be even better in C++20, which has basically the format lib built into it. I'm tickled pink. I've been using format lib for a number of years, so it's good that it's going to be part of the standard. I liked it. Okay, we have been at it for an hour. I'm taking a 5-minute break to get me something to drink, and then we're going into the really obscure C++ topics. Okay, recording is still on. My sound should be back. If you only see me move my mouth, then let me know. Smart pointers. So C doesn't really have pointers. C has addresses. Whoops. Yeah. C pointers are barely needed, the star thingamies in C++, because if you're doing arrays, use vector. If you're doing character buffers, use string. Now, the only time that you really need pointers is if there is a matter of ownership. If really two names refer to the same thing. And that doesn't happen a whole lot. One case is, for instance, linked lists. But there are more cases. General graph theory. If you have a graph, directed acyclic graph, in general, and any recursive data structure, you cannot say a node in the graph contains another node, because that would blow up recursively. So you have to say a node contains a pointer to another node. Okay, so that sort of thing is the only time that you really need actual pointers. Okay, pointers. So C++ and Fortran have an actual nice pointer concept where a reference or a pointer is an alias C, and inherited by C++ has a basic pointer concept where a pointer is not really an alias, it's the address of some object. If you're writing C++, probably you should not use the old C mechanism, and that last sentence doesn't belong here. Okay, so you already know that references are better than passing by address. Okay, let's look at smart pointers. Let's make a class hasX, which has an X. So you create it in the usual way. There's a value function that gives you the stuff back. So normally if you have an actual object, so you have your X object, and then you do x object dot value. Okay, object dot, and my output is messed up again. Really, I've been basically the past 4 days in Austin were disastrous. My power went out early Monday morning, was back for Tuesday afternoon, and then out again till late yesterday afternoon. So I haven't done anything over the last couple of days. Let's use that as an excuse for a couple of blemishes on this lecture. Yeah. If you have an object, then the dot notation gives you methods and maybe data members. Okay, now this is a weird notation. Instead of having an x object, we have an x pointer. How do you make a pointer? You have a new magic word, make shared. So I'm only going to show you shared pointers. There are shared pointers, unique pointers, and weak pointers. But I'm only going to show you the shared pointers. They are intuitively the easiest to work with. So make a shared pointer to a hasX object, and then the 5 that comes after it is the arguments to the constructor. So object 5, shared pointer to hasX, also 5. Okay, now if you have an object, then you have the dot notation. If you have a pointer, then we use the same notation as in C for address of struct. C programmers, everyone knows the arrow notation. That's dereference followed by dot. So if you have a pointer, then instead of the dot notation, you use the dash greater arrow like notation, and that gives you the value. So anything like getting the value, setting the value, it's all the same except that the dot is replaced by the arrow. Okay, so introducing a pointer only gives you a slightly baffling syntax when you create the thing. Okay, so what is happening here? Okay, so instead of having an object, you have something of type shared pointer to object is make shared pointer to blah, blah, blah. Well, the compiler can figure out what the type of the object is. Hence, I was saying auto make shared object. So this gives you a shared pointer to an object. And so the actual type is this, but I didn't want to spell it out. Let's not do that one. You can actually dereference it if you want to go from the pointer to the actual thing that's under it, and there is the get function. Let's not do that. Okay, yeah, pointers and addresses don't go together. This is some code and you get a bizarre error message. So really smart pointers only go with C++ object-oriented programming. Now, why do you do this stuff? So now we have to go into a memory management, and we have to take a step back. So vectors are like any other variable. They are created inside a scope. So you say vector of int v, and then that v lives in a program unit or in the true branch of a conditional. Anyway, vectors have a scope, and so when you go out of that scope, the vector disappears, and so the memory is deallocated automatically. So that's yet another reason for using vectors. No memory leaks. Technically, it calls the destructor, but basically they obey scope. Now, just as with C pointers, you can malloc something inside a program unit and then assign it to a pointer outside that program unit. So dynamically created stuff does not obey scope. It is possible to create something inside a program unit and move it out. Okay, that's where memory leaks come from, or that's another possibility for memory leaks in C. You create something and you forget to deallocate it. Anything you malloc does not automatically disappear when it goes out of scope. Smart pointers take care of that. Okay, let's say I have a class and I'm going to demonstrate that smart pointers, unlike old style pointers, have no memory leak problems. So I have a constructor and the constructor only says, I'm calling the constructor. And remember that there was a destructor, which is what deallocates the data of an object when it goes out of scope or anything, or at the end of the program. So the destructor only says, I'm calling the destructor. Okay, what does that do? Now let's see how this relates to pointers. So I print set pointer. I create a pointer to a thing. And now I print, I'm going to overwrite the pointer. And indeed, I write null pointer over the thingamy. Okay, I didn't mention null pointer yet. In C, this all caps null thing is really just a plain 0. C++ has an actual null pointer. So I create a pointer to a thing. I create a pointer to a thing, and then I overwrite the pointer. In C, this would have been a memory leak because when you create the pointer, you presumably allocate the memory for the object, and it is only connected to this pointer name. So if you overwrite the thing in the pointer name, you still have that allocated memory, but you have no way of pointing at it, of finding it anymore, because the only name that pointed to it is now overwritten. Okay, so what happens here? Okay, C out, it writes set pointer. Now when I create the pointer to a thing, it creates the thing, so it says calling constructor, and then I print, I'm going to overwrite the pointer. I get that message, and now when I actually overwrite the pointer, then there is no one that's pointing at the object anymore, and so the object is automatically being destroyed. Let's call it destructed. Okay, so no memory leaks. The allocated memory has gone away. This is beautiful. And a similar story for, so a shared pointer means that multiple pointers, multiple variables can point at the same thing. So this is an example where you create 2 pointers to a thing, you overwrite 1 pointer, nothing happens, you overwrite the other pointer, and then the object gets destroyed. Read over it at home. These slides shouldn't have been here. They are not good. Anyway, in the latest version of the textbook, there is a better chapter on linked lists. So if you want to see how to do linked lists, read the textbooks. These slides are not the best. Sorry. Advanced pointer topics. Yeah, there's an any. So I don't know how many people here are in the habit of regularly writing void star. I've been guilty of that quite a bit. C++ has a better mechanism. Okay, I mentioned the null pointers. Okay, we go into more obscure stuff, namespaces. So what's happening here? What is this standard stuff? Okay, if you only say include vector, then suddenly your program knows about vector, but vector is in the standard namespace, so you'd have to spell it out, standard vector. Now, some people do the following. They say include vector, and by default use the namespace standard. And so now if you write vector, then the compiler tries to find the definition of vector in the standard namespace. This can be good, this can be bad. It's convenient. So what I've been doing in the programs so far is instead of using namespace, I only say using standard vector, which means if in the future I am saying vector, then that refers to the standard vector. And if you do that, then okay, the problem with this approach is that the namespace standard has hundreds of names. And so maybe there will be a conflict with something that you write. So I don't like this approach. It's good for student programs, but not for serious code. I much rather write using standard vector. Here's an example of something that once went wrong in the class that I was teaching. Regardless, never put using in a header file. Okay, these namespaces, if you start writing C++, then the only namespace you'll come across is namespace standard. So why all the fuss? Well, you may want to make your own namespace. So that name vector is a very attractive name. You may want to make your own vector, as in a vector of whatever physical thing, but you want your own vector still to be able to use the standard vector as a component. Okay, so that's where the namespaces come in. Now you can spell out, if I say vector, I mean my vector, or if I say vector, I mean the standard vector. And so it becomes possible to have two classes, both named vector, in the same program. Okay, you write namespace, and now you can say, okay, object from a namespace, or if you say by default I'm using the namespace, then you have the object. Or you can say, okay, from this new namespace, if I say an object that comes from there. Oh, you can even do fun things. You can have nested namespaces, and now you can say that using namespace ABC is really space A and then subspace B, subspace C. I've never had a program that was big enough that I needed multiple spaces, but lately I've been dealing with Intel's latest one API SYCL, the Data Parallel C++ library, which has its own definition of cout. And so I really need to be careful if I say standard cout or SYCL cout. Okay, so this sort of collisions sometimes happen. Namespaces. Templates. Okay, you finally learn what the angle notation is about. So sometimes you have multiple functions that do sort of the same, but on multiple types. For instance, you may want to have a stack or a queue of integers, and you may want to have a queue of doubles. And so both are the same, are sort of the same object class functionality. It's just that they have different types. A queue of integers internally stores integers. A queue of doubles internally stores doubles. So should you duplicate the same code twice? So you write all that you need for integers and then you copy paste it to doubles and you edit it? No, that's where templates come in. So you say, okay, template, I'm going to use a type name, and people usually just write T rather than your type variable. So in what comes next, your type variable is a type variable. So whenever you see that, it stands for a type, but unspecified. Okay, so let me show you an example. So I write template type name T, and now I have a function that takes a T and it outputs that thing. Okay, this is sort of pointless, but it illustrates it that I'm defining two different or multiple different functions depending on their input name. See, I can have an int, and then I call the int function. I can have a double, and I call the double function. And the code behaves as if polymorphically I had defined one integer function and one double function. Now, this is still a pretty simple example, but feel free to do this exercise at home. So I want you to write a function epsilon, which computes the machine precision. And so if you call epsilon with a floating point number, then it says machine precision is 10 to the minus 7. And if you call epsilon with a double, then it says machine precision is 10 to the minus 15. Everyone knows what machine precision is? If not, search for my HPC book. Okay, so yeah, and there are plenty of other examples of templating. So with templating, the actual type becomes a variable. And so you've seen that this angle notation with vectors. So the standard template library, STL, this is a gross distortion of the truth, gross simplification. It acts like there is a class vector, but it's a vector of type name. And so internally it stores an array of t's, and the add function returns a t. Okay, so the whole definition of vector is templated with the type. So that's why it was a vector of int, vector of double, and the code was only written once, but thanks to templating, they act like separate definitions. Okay, more obscure, more higher C++ stuff. If your code misbehaves, then you can throw an exception, which is kind of a nice way of dealing with errors. I'm not sure how you would do that in C. Probably use a system function, use a signal. So the fun part about exceptions is that you can catch them. Two new keywords, try and catch. So you surround the potentially dangerous code with try catch. And if you know that this function, here I said throw 5. So your function, if something goes wrong, I throw a 5. So now the catch clause can say, okay, I catch an integer, and if something went wrong, then that integer is my error code. See, nice, clean error reporting. Yeah, so when I teach this as a class, then I make the students do a sequence of exercises related to prime numbers. Remember that just before noon I told you, for yourself, try writing a prime number generator class. So you have your prime number generator class, and you keep calling next prime. You keep calling it while true, but you catch a string, and for instance, the string says, hey, I'm reaching max int. So you can define your own error conditions and you can catch them. If routines can throw different types of errors, then you can have different catches. And literally 3 dots means catch anything. Yeah. Let's not do iterators. Let's talk about auto. So interrupt me if anyone has any questions. This is a lot of material. Yeah, okay, so if you have a address of a vector of shared pointers to a class and you create it like that, this is not the best example, but if you have complicated types, then the compiler can figure it out and just say, okay, auto. Oh yes, you can even use auto for the return type. This is strictly C++ 17. The expression I equals j is a Boolean expression, and so the return type of this function is bool. This is sometimes convenient in object-oriented programming. You can even have auto reference. Yeah, auto. This is a subject I wanted to get to. This is really cool. Lambdas or closures. For the couple of Python programmers, Python has lambda, right? You've used that? Have you done a reduction with a custom lambda? So Python has lambdas, and lambda comes from Alonzo Church, who in 1930 settled the Entscheidungsproblem, the decision problem, something theoretical in mathematics. Anyway, in order to settle this big open question, he invented lambda calculus, and after him, for the last 80 years, functions have been named lambda. Lisp has had this, of course, since 1970. Okay, what are we doing here? We are creating functions that don't have a name. So to start with a pointless example, and you recognize lambdas by the use of square brackets outside of an array context. So function of 2 floats yielding a float is defined as return x plus y. And so this whole thing is the same as saying f, where f is that function. And so you can apply this to something. So you have a function of 2 floats, and you apply it to 2 floats. Ta-da. Okay, this is pointless. But for the next step, you can now actually have a function variable. So summing is this function, and now you can apply summing to two floats. You could sort of do this in C with function pointers. Oh, so let's. What I in the two examples so far, the square brackets have been empty, but what happens here is a capture clause. So if you make a lambda expression like this, then you can capture variables outside of the environment and they become part of the function. So you know that in C you have the power function, which is a number to an exponent. Okay, so now I want to make a function that is the function to the power 5, which has only one argument, x to the power 5, or power 5 of x. So I want to make a function power 5, which takes a float, x, and returns x to that power. And you do that by, so this number 5 that you want to define it with is in the environment, and then you capture it. And so now you have a function that computes, it's a function of only one variable that computes x to the power whatever exponent was when you defined the function. Okay, so what does this look like? You have that code there, and now you do for float whatever x power 5, so power 5 of x, and now you get the output 1 to the power 5 is 1, 2 to the power 5 is 32, etc., etc. Okay, so this is pretty flexible, and you cannot do this with C function pointers. So right, capture and then the function definition. Okay, so this example is a lot of code, but I want to have a class called selected ints, and so it's a collection of integers, vector of int, bag, except that there is a function, a Boolean function of an int that says yes, this goes into the bag, and no, this doesn't go into the bag. Is the association of capture values to the lambda fixed? Michael, yes, because your function can, as I'll show you in the next slide, your function can transcend the scope where the capture variable was defined. So yes, it is fixed. At the moment that the function gets defined, this variable exponent is frozen and baked into the function. Good question. So I hope you recognize the syntax bool of int. It means a function of one int returning a bool. And you haven't seen this one yet, but if you want to put a lambda in your class, then you need to write it like this. So let me show you how it's used. So we make an object multiples, which is a selected ints thing. There is a divisor, and so I want my object multiples to only contain the multiples of the divisor. So I create my object with a lambda function that says, okay, if you give me an int I, then I will tell you if this thing is acceptable, namely if I modulo divisor equals 0, then it is acceptable. And now I loop through I is 1 to 50, and I add only the multiples of something. So give a multiple, give a divisor 7, and now I go through 1 through 50, and only the integers for which this test is true get added, and indeed I get the multiples of 7. So this code supports the whole thing. Study that if you want to. Okay, so if you want to practice your lambda skills, here is a good exercise. Did you know that old computers did not have a square root instruction? They had multiply and divide. How do you do square roots if you only have multiply and divide? Well, you implement Newton's method. Okay, so so suppose you want to compute the square root of y, then you now make a function f of x is x squared minus y, and you try to find the x for which this function is 0. That's Newton. Okay, so you make a function fy which captures y, and then you do the Newton method. Okay, so this is the background knowledge, and now write a root finder method which needs two functions, f and f prime, that are both double of double. And it's kind of a mind blower, this exercise, but it's a good exercise. So where in practice do you use lambdas? Well, in the C++ library, and I don't think I'm going to go into that in detail. There are things like functions that on an array ask, does any element satisfy something, some predicate? And that predicate you specify with a lambda. Okay, so it tells you, does any element satisfy a predicate? And the easiest way of specifying the predicate is doing it with a lambda. Okay, lambdas are really cool. C++ casts. They are so hard to search for with an editor. What on earth do you search for with a cast? It's paren, and in the middle any existing type, or even any struct type. C++ casts are much more explicit. So if you want to cast something to int, you now write static cast to int of whatever number. So C++ has a number of different casts. Go away. The old style C cast is really, okay, here is a byte in memory, and I'm going to completely ignore what type it is, just pretend it is type this. This is very dangerous, but yeah, well, I don't know how many of you daily work with code with opaque handles, yeah, casting left and right. If you do it carefully, you can do pretty cool stuff with it. Okay, static C++ has several casts, and that is because if you start working object-orientedly, and you have a base class and a derived class, the derived class usually has more data, and it is not like this block in memory is the base information and then the rest is below it. No, it actually goes like this. And so if you have the beginning you have the beginning of your derived object and you say, no, I cast it to a base object, then the memory doesn't fit. So C-style casts are extremely dangerous in C++. Static cast is for scalar stuff. Static cast based to derived, I wouldn't do that. Dynamic cast is the safe way of casting between base and derived classes. We haven't talked much about const, but there is a const cast. If something is a const object, then you can make it a non-const object. But searching for these keywords with an editor is much easier, so I don't mind a couple of extra characters. Static cast, illustrations of casting. Okay, we have been getting into really complicated stuff here. Let me show you a couple of simple things that really might make life more elegant and simple in C++, and then we'll call it a day. Still 40 slides to go. Yeah, so if you're used to writing in Python, you can have a function that returns I, x. So you have an integer I, double x, and you just say I, x and return that. And then the calling environment says catch it. This makes my Python programming life pretty easy. And C++, in C++, you could sort of do this. In C++ 11, you could say, okay, if I want to package an int and a double together, I declare a standard tuple of int double. And then if you want to extract the double, you would say, okay, get member number 1 and print that out. Or if you wanted the integer member, get member number 0 from that integer double thing. This is just a very inelegant notation. In 17, this got way better. So, okay, so suppose you have a function that, okay, the example is you have a root function, but you want to somehow signal an error if you apply it on a negative number. So maybe root. And so what does maybe root return? It returns a boolean saying, yes, I was able to take the root, and it returns a float saying, this is the actual root. Okay, so maybe root is called with a float x, and if x is negative, then you return a tuple of bool and float, namely false and -1. The -1 is regardless, but whatever. And if x is non-negative, then you return a tuple of true and the square root. Okay, so that looks decent. Oh, yes, and because make tuple is a standard library function, you can actually do auto, and you don't have to spell out what the type is of your function. You can just tell the compiler, you can figure out what the return type of the function is. The other way of doing it is to say explicitly, okay, this function returns a bool and a float, and if I cannot take the square root, I return this, which is a tuple of a bool and a float, and if I can take the square root, I return this. Okay, so now it's starting to look elegant. Python has no type system, unless you're on 3.8 and you use that experimental thingamy. But in C++, you need to spell out types. So at some point, you'll have to say, okay, I'm dealing with bool float tuples. But then how you construct them is pretty elegant. Right, so this is almost as good as Python saying return false comma -1. And oh, I should have marked that this is 17 only. This is a recent innovation. So writing the function that returns the tuple is now pretty elegant. And on the other side, it's really nice. You now say auto succeed comma y is the maybe root of x, where succeed is the boolean and y is the root. So you don't have to separately define saying, you don't have to define succeed is a boolean, y is a float. The auto definition completely takes care of it. This is known as structured binding, and it is pretty nifty. Now, in this particular case, the case of a Boolean that said, yes, it was possible, and then the result, you don't actually need the Boolean. You need the result and a way of asking, was this result valid? Okay, so that's where you, instead of having a tuple, because I mean, in the case where it did succeed, the true is superfluous, and in the case when it did not succeed, the -1 was superfluous. So this is kind of over specification. So a new thing is optional. So you say this function may be root, returns an optional float. Namely, if x is less than 0, then it returns and now I'm blanking. Brace is shorthand for something. I hope it's on the next slide because I can't remember. It's short for something. But basically this means it's not a float. So an optional float, in this case, it's not a float. And in the case where it did work, then you just return the float that you wanted to return. Okay. So for x in 2 comma -2, and I'm using again a couple of things. The dot f means float. It's redundant, and the parentheses here, you have seen that before. This is an initializer list, so this actually creates a vector of length 2 with the numbers 2 -2 in it, except that I don't have to say vector, I don't have to say what type, and I don't have to worry about, so this is a vector denotation. So for x in 2 comma -2, and here I'm using the initializer clause of the conditional, so root becomes a minus root of x, and the actual type, of course, is an optional float. It's not a float, it's an optional float. So what do you do? Root becomes an optional float. If the root has a value, then, oh, and here is finally a legitimate use of the C dereference star. So that's how you get the value. Oh, you can actually say root dot value. Okay, and if your optional float did not have a value, then you say I could not take the root. Okay, so between structured binding for tuples and optional, some simple code becomes a lot more elegant. Const, yeah. Okay, so it is a good idea when you start doing object-oriented programming to indicate if functions are const. So not only can you have const on parameters, meaning I promise that I'm not going to change this parameter, you can have functions that are const. And so here I have a class with a method, whatever, and by saying const, I say this function will not change any of the data members of my object. So it's purely functional. And if you are consistent with this, and it is a little bit of a burden in the beginning, if you are consistent in doing this, it actually helps you catch programming errors. So the C++ community has a bunch of these slogans of what the current way of thinking is, and the thinking here is const always. Let's see. Yeah, const even becomes part of the type, and so you can have a function add without const, and you can have a function add with const, and they do something slightly different. Details. Oh, this is yeah. Const expr. So the C++ compiler is getting very sophisticated. If you think that an expression can actually be evaluated by the compiler, then you can mark it as const expr, and then the compiler will eliminate dead code. You can do sophisticated stuff with this. So if you have a case statement, which ultimately depends on stuff that is deducible by the compiler, then the case statement can be completely collapsed to only the relevant case if you do this const expr trick. Let's see what more. Iterators. Oh, yes. I personally don't use this terribly much, but you see many tutorials and Stack Overflow questions answers that use it, so I'll just mention it. If you have a vector or or a number of related classes that you can iterate over, then there is a begin method and then there is an end method. Begin is sort of a pointer to the first element, and end is a pointer to just after the last element. And begin gives you, so you say pointer equals begin, and then you say star pointer, so you may think that pointer is a C style pointer, but it's not. It's an object for which the star operator is defined. Subtlety, but I once ran into it. Anyway, but yeah, so this is called an iterator, and iterators allow you to do pointer arithmetic, so you can increment them. So you start at the beginning of the vector, and the plus plus gives you the next element of the vector, minus minus, and a bunch more things. So yeah, using iterators, you can do things like erase elements of a vector. For that, you really need iterators. There's no other way of doing it. What I wanted to show, and there's stuff like accumulate, huh. I thought there was a slide on, huh. Okay, a couple slides missing. In that case, we're just doing a couple of simple things. In C, there is a limits header, and C++ is better. So you can ask for limits, meaning the biggest and smallest number. And so you ask for the limits on the long int type. What is the maximum long int? Min, max, printing out a couple things. For float and double, there is a min in the sense of most negative. There is a min with underflow and a min without underflow. So, but basically all this stuff is now nicely, cleanly available. There is an epsilon function. Yes, there is an epsilon function. Oh, this appeared earlier in the slide. Everyone knows what epsilon and machine functions, machine precision are. Yeah, no time to go into that. Read my HPC book. Yep, thank you. Okay, so the limits are kind of obscure, but I wanted to mention two other things. Random, the C random number generator is of course available in C++, but it's really a steaming pile of doo-doo. It's not really good. C++ has a much better random number generator. So it unfortunately is a little complicated. You create a random device, and then you make a random engine, and then you declare a distribution, so Poisson, whatever. And of course, if you make a distribution over integers, you can do things like throwing a dice. So that's much more elegant than doing a random number and then rounding it to 0, 6 or 1, 6. So you make a distribution and then, okay, you say, okay, I want something in this distribution coming from this generator. And so that's how you make random numbers in C++. And so, for instance, throwing the dice is a uniform int distribution from 1 to 6. Oh, okay, that's the only example I give. There's a lot more. So all of this is in the chapter of my notes on the standard template library, and I have a book on my shelf that is literally way over 1,000 pages. It is only about the standard template library. So it's not about the language C++, it's just about all these things. But I wanted to mention random and time. So time is always a headache. You have to look up the man page for get R usage or time of day. What's available in C++ is a couple of clocks, and they come out of the chrono header. So you could say, okay, my clock is a high resolution clock, and now you I don't even bother writing down the exact type. Just say my clock is now, and then duration is another thing. So these are not floats; they are nice types. It's a chrono timestamp, and duration is a chrono duration. So if you subtract two timestamps from each other, you get a duration, and now you can. Yeah, I have not memorized this. I always have to copy it from my notes. So if you have a duration, I think a duration is a floating point number, but if you want to cast it to microseconds, then you do chrono duration cast, templated to chrono microseconds, and that gives you the number of microseconds, except that it's not actually the number, and you need to take the count of it. So yeah, it's a much better random number generator. I think it's a Mersenne twister. And it's a bit of a hassle to use, but it's much better than the C timing. Curiously enough, just supporting the date is even trickier than time, and so it's only in C++20 that there is a good date function. Like I said, date coming in C++20. File system. Okay, so I used to think that running through a file system is a Python job, but it is actually available in C++ for a long time. Yeah, yeah. So modern versions of C++ 17. Oh, I don't even give an example of this. Regular expressions, yet another Python job. Nope. The C mechanism is actually not bad. Take a look at the slides. And that brings us pretty much to the end of a pretty full day of C++ing. So I'll just recapitulate that the default for any compiler is 98 or 03 standard, which really counts as archaic C++. There's a couple of features like auto pointer, which are now abandoned. They're deprecated. My notes say that C++ compilers will even give an error on it. C++ 11 was the first modern C, so it had auto, range-based for, lambdas, a couple other things. 14 got a little smarter on auto stuff. A lot of the improvements were in templating, which I don't do all that much, but so 14 was not terribly important to me. 17 had things like optional structured bindings and the init clause. Sorry, my missing references are to sections in the textbook. So 17 made a number of things much cleaner. I don't know when chrono and random were finalized. Anyway, and now upcoming C++ 20. Oh, I think I asked an hour ago if there were any people programming Fortran here, and I didn't get a response. So if you write modern Fortran, you know about modules. Modules are a much cleaner way of dealing with what C does with header files. And C++ 20 now has modules. Yay. Oh, a topic that I completely, utterly skipped is threading. So modern C++ has threads and mutexes, and C++ 20 then adds coroutines. I really need to do some experimenting to see how efficient threading is compared to OpenMP, which is my preferred way of doing threading. Which is why I assume that everyone attending here is engineering or scientific programming. And so I don't think C++ threading is terribly relevant for you, which is why I didn't mention it. But for systems programming, and if you want to write a web server, I'm sure that C++ threading is very relevant. Concepts is something obscure. The spaceship operator, yeah. I don't remember what this referred to. Oh, the ranges. Those are really cool. So come back in a year when C++ 20 has been available at TAC, we hope, and I'll tell you about ranges. Time calendars, time zones, yes, that was hard to figure out. The format lib will become part of C++, so that makes outputting a little more elegant. Basically, it makes it look like F strings in Python. And finally, span, which I kind of like. And that's it. Yay! Almost exactly from 9 to 3 as advertised with a small break. Okay, so I posted in the chat a couple times this link to a download location of my PDFs. You can also take note of this link, which is a link to all 3 of my textbooks. So what I've been presenting here today is really based on the textbooks. So the slides give you the quick Reader's Digest version, but if you want to read it in sentences and paragraphs, then take a look at the textbooks. Whew, that's it. Any questions? How many people are still here? 14. Not bad. Going once, going twice. Okay. You're welcome, everyone. Yeah, so I've been taking notes on a couple of typos and stuff in my slides. But if you see things that are unclear or typos, feel free to contact me. And if you have questions about C++, you can contact me over email. Is my email on the title slide? No, it is not. Okay, you can find me in tag directory. Okay, thanks for sticking with me to the end. I hope this has been useful, and as we say, stop coding C. C++ is better. Okay, that's it. Have a nice weekend. Stay warm.
Bye. Thank you. Have a nice weekend.
You too.